Welcome to Chapter 3, Video 2, Truth Table Tests for Semantic Properties. In the last video, we learned how to construct basic truth tables. In this video, we're going to learn how to use that method to test for the various semantic properties of formulas, pairs of formulas, sets of formulas, and arguments.
Calculating all possible values for a random selection of formulas is not the most exciting thing in the world, but we can put this method to use to answer some interesting questions about various formulas, sets of formulas, and arguments. For example, check out this formula. Now, here we have only one distinct atomic component, and 2 to the 1 is 2, so we're only going to have 2 rows in our truth table, so we just need to build this basis column. And though it may seem a little oversimplified, I am going to copy these over just so we can see exactly what's going on. Now, the main connective here is the disjunction, but we need to calculate the negation before calculating the disjunction. Of course, this is simple, it's just a negation, so for where A is true, not A is false, and where A is false, not A is true. And then to calculate under the main connective, we've got a disjunction. So as long as one or both sides are true, the whole thing is true. So we'll get a true there and a true there. And if we put our box around that, we'll see that something mildly interesting has occurred. This sentence is never false. No matter what the value of its atomic component, it always comes up true. In fact, we'll call this a truth functionally true statement. It is always true in virtue of its truth functional structure. I'll put a definition of that up in just a second. I want to show you a contrasting case. Here's a formula that has 2 distinct basic components, B and C, so it's going to have 4 rows in the basis columns. And if we copy the basis columns over very quickly, you'll notice that the main connective is here, the biconditional. We can easily calculate the values on the left side of the biconditional with the conjunction B and C, where they're both true. The conjunction is true, where at least one is false. They're all false. Now to calculate the other side, we need to take care of the negation. So C goes TF, TF, so not C is going to go F, T, F, T. B goes T, T, F, F, so not B is going to go F, F, T, T. And then looking at those 2 remaining columns there, we can calculate the value of the disjunction. We've got an F and an F, which is the only way a disjunction comes up false. We've got an F and a T, the T makes it true, a T and an F, and 2 T's. So now we're looking here and here to calculate the value of the whole, and we've got T and F on a biconditional makes it false, F and T makes it false. In fact, the remaining 3 rows all are F and T. Here we have what we call a truth functionally false formula. No matter what the values of the atomic components, this formula always comes up false because of its truth functional structure. One last example. Let's just take the following 2 distinct atomic components. Once we fill in the basic columns, we can see in the first row we have true antecedent, true consequent. That will give us a true. False antecedent, true consequent. Again a true. True antecedent, false consequent. That gives us a false. False antecedent, false consequent gives us a true. So we have 3 different formulas here. We have one right here that can never be false, it must always be true. One right here that can never be true, it must always be false. And one right here that is sometimes true and sometimes false. It won't surprise you to learn that we have special terminology for each of these three cases. So the definition of the first case, a truth functionally true formula, remember WFF is an abbreviation for well-formed formula, and we pronounce it WIF. A truth functionally true formula is one in which the formula is true on every truth value assignment. Remember, each row of the truth table represents one possible truth value assignment to the basic components. How do we know if the formula is true on every truth value assignment? We construct a truth table and we look and see it is in fact true on every truth value assignment. That is the test right here. So we can tell if only t's appear in the column under the main connective, then it's a truth functionally true formula. Note, it does not have to be every column, only the main connective. Contrast that with the next example, truth functionally false formula. A formula P of S is truth functionally false if and only if P is false on every truth value assignment. Well, what that means is if and only if only F's appear in the column under the main connective. And that's exactly what we have there. Truth functional contingency is the case where you have some T's and some F's, as in the third example here. There are two further definitions we'll be interested in for individual formulas as well. The first is a truth functionally satisfiable formula. A formula is satisfiable if and only if there's at least one truth value assignment that would make it true. That is, if and only if it's not truth functionally false. So it's actually the case that both the first and the third examples here are truth functionally satisfiable. Neither of them is truth functionally false. They each have at least one T in the column under the main connective in their truth table. The notion here is basically that it can be true. The other is truth functionally falsifiable. A formula is truth functionally falsifiable if and only if it's not truth functionally true. That is, it's false on at least one truth value assignment. It can be false. And we see that this is the case here and here. So what we wind up here is the following situation. The first formula is truth functionally, and that T-fly is my little abbreviation for truth functionally, so I don't have to write the whole long thing out. It's truth functionally true and truth functionally satisfiable. The second example here is truth functionally false and truth functionally falsifiable. While the third is truth functionally contingent and truth functionally satisfiable and truth functionally falsifiable. In fact, any individual truth functional formula will fall into one of these three groupings: truth functionally true and satisfiable, truth functionally false and falsifiable, or truth functionally contingent and therefore truth functionally satisfiable and truth functionally falsifiable. Here's a little diagram to remind you of the interrelationship between these categories. The three down the center are mutually exclusive. So remember, truth functionally true means all t's under main connective. Truth functionally false means all f's under main connective. And truth functionally contingent, some t's, some f's. But of course, if you have a sentence that's either truth functionally true or truth functionally contingent, then it's truth functionally satisfiable because it's going to have at least one t, and of course more if it's truth functionally true. But again, if it's truth functionally false and truth functionally contingent, then it has at least one f under its main connective, so it's truth functionally falsifiable. In addition to considering formulas in isolation, we can look at pairs of formulas. For example, let's take the following. Not C and B, and either not C or not B. We can do a joint truth table for these two formulas in essentially the same way we do a truth table for individual formulas. We draw a horizontal line, draw a vertical line. We've got two distinct atomic components here. We'll put them in alphabetical order, make the basis columns. Copy the basis columns over very quickly. We'll start on the left-hand side. We need to calculate the value of the conjunction before getting to the main connective. So 2 trues makes this true, a false makes this false, a false makes this false, and a false makes this false. So we're done here. We use that column to calculate the values under the negation, which is the main connective for this formula, and we'll get false, true, true, true. Box that. Go over to the right-hand side. We've got to calculate these two negations. We can do that quickly. Use those two columns to calculate the disjunction. 2 false under the disjunction make it false. A true and a false makes it true. A false and a true makes it true. And 2 trues makes it true. Box that column. Now if we compare these two formulas, we'll see that on each row of the truth table, they match each other. We've got F and F, and then the rest of the way down we've got T and T, T and T, T and T. So in each row under the main connective, these formula match. So for these two formulas, they have the exact same pattern under their main connective. We'll say of these that they're truth functionally equivalent formulas. Let's take this, shrink it down a teeny bit, move it out of the way, and let's look at another example. So 2 simple sentences, G arrow E, not E, and G. We can generate a joint truth table. Copy over the basis columns. Let's start again on the left. We've got a conditional here. So where both antecedent and consequent are true, the whole thing is true. False antecedent, true consequent makes the whole thing true. True antecedent, false consequent, that's the case that makes it false. And then false antecedent, false consequent makes it true. Now, to calculate this conjunction, we need the value for the hook on the E, so that's easy enough. We go F, F, T, T. Let's get this out of the way. So focusing on those two columns, with a conjunction, we have an F. That makes the whole thing false. 2 F's makes the whole thing false. 2 trues makes the whole thing true. And then true and a false makes the whole thing false. Now, if we look here, we've got a situation where the columns under the main connectives are the inverse of each other. Wherever one has true, the other has false. So what we've got here are truth functionally contradictory formulas. Now we have one last case we can look at. Take these two formulas. Now, when you get more and more proficient at this, you can skip the step where you copy the basis columns over. For example, these two formulas are so simple that we probably don't need to copy the basis columns over. We just pay attention to what we're doing here. So with A and B, that's only going to be true in the case where both sides are true. So we'll get this pattern. B or A, that's only going to be false where they're both false, so we'll get this pattern. Now you notice that the columns under the main connectors of these formulas neither match nor are they opposite. In some cases we have the same value, and in some cases we have opposite values. So what we say here is that this pair of sentences is neither truth functionally equivalent nor truth functionally contradictory. Let me put the definitions of these concepts up. So what we have here now on the left are three joint truth tables. In each case what we're doing is comparing a pair of formulas. In the first one we see that the columns under the main connectives match. So the two formulas are truth functionally equivalent. In the second case, the columns under the main connectives are opposites. So what we have there is a truth functionally contradictory pair of formulas. And in the third case, what we've got is neither truth functional equivalence nor truth functional contradiction. Now, another property we can test for is consistency of a set of formulas. What we mean here is a set gamma of formulas is truth functionally consistent if and only if there's at least one truth value assignment on which all members of the set are true. We do this by generating a large joint truth table and looking at the values under the main connectives of all the formulas in the set. If there's one truth value assignment on which they all turn out to be true, then that set is consistent. If there is no such row, that is, there's no way for all the formulas to be true at the same time, then the set is inconsistent. Let's take a look. Let's take this set of three formulas. Now a set can actually have any number of formulas in it, from none to an infinite number. When we're working with truth tables, of course, we can't do a truth table for an empty set, and we can't do a truth table for an infinitely large set. So we would, in principle, only ever be dealing with a finite positive number of formulas in a set. What we do is we generate a truth table for these three formulas. We will list them. Now we have three distinct basic components here, so we're going to have 8 rows to this truth table. So we'll generate the basis columns like so. And if we look at the leftmost of the formula, C arrow D, and we pay attention to these two columns here, we can see on the first row we've got true antecedent, true consequent, which gives us a true. Again on the second row. Then we have true antecedent, false consequent, which gives us an F. True antecedent, false consequent again. And the rest of the way down we have a false antecedent. So no matter what the consequent is, the formula is going to be true. Now, for the second one, we need to pay attention initially to the E and the D column. E alternates TF, TF, so I'm going to put under the hook here. Now, taking those two columns into account, we're looking for places where they match for a true or do not match for a false. So we'll have a false there, true there, true there, false there, false there, true there, true there, false there. So we've got two of our columns done. Now if we look at the E column and the C column, working with conjunction here, it's only going to be true when they're both true. They're both true in the first row, but then E is false. They're both true in the third row, but then E is false. And then C is false the rest of the way down, which is going to make the whole conjunction false. Now, is this set consistent? Well, we need to see if there's any row of the table on which there is a true under every one of the members of the set. And in fact, that never happens. In the first row we have a false here, second row we have a false here, third row we have a false here, fourth row we have 3 falses, fifth row we have a false there, and then there are falses there. So there is no row in which every member of this set is true. So what we have here is a truth functionally inconsistent set. Now we'll shrink that down a little bit and try another example. Let's take this set. Again, I'm just going to use 3 sentences here to keep this brief, but notice we only have 2 distinct atomic components here, so it'll be a slightly smaller table. So if we list these out, now if we look carefully here, we'll find that in the third row, where A is false and B is true, the first sentence is true, the second sentence is true, and the third sentence is true. So there is a truth value assignment on which every member of the set is true. So this set is truth functionally consistent.
Now we have 2 more important truth functional properties that we want to be able to test with the truth table. Truth functional entailment and truth functional validity. If you recall from chapter 1, these are essentially the same sort of notion, except that entailment can apply to infinitely large sets and target statement. But with truth tables, we'll of course only be able to apply the test to finite sets. The procedure for testing for truth functional entailment and truth functional validity are essentially the same. Consider the set here with the target statement not K. The claim is that the set does entail the target statement. Compare that to the argument using the same formulas here. The members of the set are the premises, and the claim is that the conclusion, not K, follows. Well, what we're going to do is construct a joint truth table involving all 3 of the formulas involved, and then in each case look to determine whether we have a situation where the members of the set or the premises are all true, but the target or conclusion comes up false. If we do have a truth value assignment in our joint truth table where we get true for every member of the set and false for the target statement, which would be the same thing as true for all of the premises and false for the conclusion, if that happens, then the target is not entailed and the argument would be invalid. If, however, we don't find such a situation, then we'll have the set entailing the target sentence, and we'll have a valid argument. So let's do the truth table and see what happens. Here now we have a joint truth table which will function to test both the entailment claim, since we have both members of the set listed and the target formula listed, and it serves to test the argument for validity, since we have both premises listed and the conclusion listed. Now keep in mind, what we're looking for is a row on the truth table where every member of the set or all the premises are true, but the target or conclusion comes up false. If we can find such a truth value assignment, then the entailment fails and the argument would be invalid. So let's take a look. As a matter of fact, there is no such row. That is, there is no row where the first two sentences come up true and the target or conclusion comes up false. That means that the entailment holds and that the argument is truth functionally valid. Now you may notice that in the fourth row of the truth table, both members of the set, both the premises, are true, and the target formula, the conclusion, is also true. But this doesn't actually matter. As you'll remember, failure of entailment and a truth functionally invalid argument could have true premises with a true conclusion. It's the presence or absence of all members of the set true and the target sentence false, or all the premises true and the conclusion false. In this case, it is absent. That's what's decisive. So we have entailment and we have validity. Consider now a different entailment claim and its corresponding argument. Again, I've given it just two premises here to keep it relatively simple. And if we set up a joint truth table for this, it will look like the following. Now, if you look at this joint truth table for both the entailment claim and the argument, you'll see very clearly that in the third row, when B is false and C is true, we have a situation where every member of the set is true, but the target statement is false, which is, of course, exactly the same situation where all the premises are true, but the conclusion is false. So in this case, we do have a situation where we find the true for however many members of the set or premises there are, and then a false for the target or conclusion. That means that there is no entailment from the set to the target formula, and it means that the argument is truth functionally invalid. Again, it is the presence or absence of all members of the set true and the target false, or all premises of the argument true and the conclusion false. Presence or absence of that decides the question of entailment or validity. And in this case, we very clearly have it, so there's no entailment, and the argument is truth functionally invalid. This concludes Chapter 3, Video 2, in which we discussed the various ways to use truth tables to test for semantic properties of formulas, pairs of formulas, sets of formulas, and arguments.